Okay, in the next section we're going to focus on looking at how conjugation and dienes and different types of structures with double bonds exist. And to begin that, we sort of have to define what it means to be conjugated or an isolated double bond and why that's kind of special. But this would be a conjugated system. So it's simply a double bond followed by a single bond followed by a double bond. If you look at the hybridization on each of these carbons, there is an open p orbital. In other words, there's an unhybridized p orbital in each of these carbons. So what that allows is it allows some delocalization or sharing of electrons, spreading of that electron wealth, shall we say, throughout these carbon centers right here. That's not happening in what we call an isolated diene. So here we've got two different double bonds, but they're separated by one or more carbons that have an sp3 signature to them. Now, those conjugated bonds, we're going to talk about some more. Don't worry, we're going to come back to that. But for this lesson, we need to start thinking about what it means to be S-trans and S-cis. Actually, this is going to be very important in a future lesson. So what this means is if you consider the single bond as a thing that you're looking at, here the double bonds are trans from each other, right? And once again here, they're cis from each other. So that's something that we're going to come back to a little bit more. If you really want to understand what's going on with conjugated or double bonds over a large area of a system, you have to look at molecular orbital theory. So go ahead and review that information, and we'll talk about that more in class too. But conjugated double bonds react a little bit differently than what we see for isolated double bonds. So things that you've looked at in the past would simply say that here we've got two isolated double bonds. We add the first HBr, then it goes to the most substituted, the H goes to the least substituted, and the second equivalent goes right there. If it's conjugated, however, you get with one equivalent of HBr, just where you expected, and then you get this crazy other product that you may not have expected. So let's look at how that relates to the mechanism. In a conjugated system, first the hydrogen is grabbed and you make a carbocation, just like you would in an isolated double bond. So I'm going to follow the pink here, ignore this for right now, and what we find is that the bromine would then go here and you would end up with a bromine exactly where you expected it. Notably, the hydrogen would be right here, right? Because that's what's happening in this first step. So the hydrogen would be on one carbon, and next door on the second carbon you would find the bromine. So we call this the 1,2 adduct, or the 1,2 product, depending on what you're looking at. Now, an alternative pathway to get to a product would be to go through what we see in the bottom. So here, what we have is that this double bond can resonate or change locations over right there, giving you this guy. Now, that also shifts where the positive charge is and where the bromine then goes, and that's how you make that crazy product. That's called the 1,4 adduct or 1,4 product, because in truth the hydrogen is here. That would be on carbon 1, 2, 3, 4. Now, I want to note a couple things here. Number one, you see how there's a double bond here that's exactly between where the double bonds over here started. That's an idea, or that should give you a clue that that's the 1,4 adduct. Also, I want to think about which one of these two compounds is most stable. Well, when you look at the stability of alkenes, you're looking for the alkene that has the most substituents coming off of it. Here we've got two hydrogens, so there's nothing really there. And here we've got one carbon. But down here we have two carbons coming off of that double bond. So in truth, this is the more stable alkene of the two. Okay, so we're going to come back to that in just a second. Before we get into too many other details, I want to just point out that this may be a little bit counterintuitive to you, because when you add HBr, the Br will not go to the most substituted here like you might have within isolated dienes, but is instead going to allow the H here and the positive charge will go here so that it's at the allylic position, because remember, resonance trumps other things when it comes to stability, and when you can have a positive charge spread over two different areas, then that's going to be more stable. Okay, so now let's go back to this mechanism that we were looking at here. We said that this is the 1,2 adduct, as you see down here, and this is the 1,4 adduct, you see here. Okay. Well, when we look at the energy diagram for these two, looking at this mechanism, doesn't it make sense that to flip this bond, it would take more energy to make that happen? Because this has a certain energy requirement right here. What the easiest thing to do would be to go boom, and there you go. But this takes a little bit of extra energy. Now, remember how we just said that this was more stable between the two of them? So even though this one puts energy in to make it happen, this guy exists at a lower energy level than this one. So when we're looking at the energy diagram, here's what it looks like. Both of them go to the same first step. So they start here, they go through a transition state. That's the highest transition state because you're going from zero charge to having something with a charge, and that puts you right here. So we both go to this position. So this arrow goes here, that represents this energy hump. You then have two alternatives. You could put less energy in and give you the 1,2 adduct, and that's what we call the kinetic product. That's the one that's formed most easily. Excuse me. Alternatively, we can put a little bit more energy in, going up a little bit higher, but it gives you a lower energy product, so you also get more energy out of the system. And that's the thermodynamic product. So when we look back at this example, the 1,2 adduct is under kinetic control. It is our kinetic product. It's kinetically favorable to get that. The 1,4 adduct is what we call the thermodynamic product. It is under thermodynamic control. Now, the kinetic product will form most rapidly, and it's going to be the major product at lower temperature. That's going to give you the 1,2 adduct. So the kinetic product will be the 1,2 product. The thermodynamic product is the most stable product, but this can be the 1,4. It could also be the 1,2 depending on what you're looking at. It's going to be the major product at higher temperatures. Let's think about this. Lower temperatures means, hey, you don't have more energy to put in, do you? And that's how you end up with the kinetic product. If it's at a higher temperature, then we can put this extra energy in, and the molecule will go at a resting state that's at overall lower energy because that's what it prefers. Okay, there we go. Thank you very much.